Okay, thank you. I'm very happy to be here to help celebrate the 10-year birthday for KIPAC. And I'll be talking about recent results from the Fermi LAT instrument and new questions that they've opened related to particle acceleration. We're very fortunate right now to have these 4 gamma ray, hard X-ray satellites all working at the same time, Integral, Swift, Fermi, and NuSTAR. There's involvement here at KIPAC in all of these, at least in the science of many of them and in the hardware and operations of a couple of them. At the same time, there's these capable ground air Cherenkov telescopes that are operating, and there's a quite bright future ahead. You know, HAWK is already being built and CTA is actively being planned. And there's this very nice plot that David Panek and colleagues put together showing the power of putting all these satellites together, plus ground-based optical and radio, on a Markarian 421 campaign. So this is an HBL-BL-LAC. You know, it peaks at high energies. You can see how well sampled these 2 components are, the synchrotron and the Compton components. It used to be very difficult to put such a campaign together. I mean, it's still not easy, but it's much easier because we have Fermi up, which is observing the whole GeV sky all the time. And Swift can respond rapidly, and it covers X-ray through UVOT, through the UV and optical. So it's much more feasible to do these kind of studies than there were in the past. This is the Fermi satellite, which has been up since 2008. And the LAT instrument, of course, you know, SLAC was a major component institution in building this instrument, and now the operations center, the Instrument Operations Center, is here. It's a really impressive instrument. It has 77 square meters of silicon detectors. It's about 20 to 30 times more sensitive than the EGRET instrument before. And I think one of the most important things that I alluded to a moment ago is that it views the whole sky all the time, every 3 hours. And so, you know, especially for time domain astronomy, it's just a beautiful tool that we're very fortunate to have. This is the most recent map, the 5-year map. It's a beautiful map. There's almost 2,000 sources in the sky. I'll show you a little bit more about that in a minute. There's a bright emission along the galactic plane. You can even see this diffuse gamma ray bubble, Fermi bubble, just shows up in the raw data here. If you look down from the north sky, you won't see the galactic plane. You realize how transient this movie doesn't play in PDF, but that's okay. What you would see if it did is flashing, every object is flashing, turning on and off, you know, with a few day time scale, some of them lasting for a week. You're really seeing the transient emission from AGN. Most of them are blazars. They're always turning on and off. They're highly variable objects. In fact, almost every object we see in the gamma ray sky, there are some exceptions like diffuse objects, but almost everyone is highly transient. From black holes to novae, blazars, certainly gamma ray bursts are the ultimate example, and even stars. We had thought the Crab Nebula would be constant. You'd think just without observing it, you would believe that it would be constant, being a magnetic gas that's emitting gamma rays. But in fact, we've discovered that it emits these flares. And so I think this is one of those objects like, where did that come from? The title of our session. Some of these are really bright. This flare in 2009, which Audrey also saw, is more than a factor of 100 in intensity compared to the steady state nebula flux. And then here's a new result from March 2013, factor of about 20. So these are, you know, really bright flares in the GeV. We were lucky during these flares because satellites did rapid target of opportunities to get Chandra, Swift, and several other observatories observing during the flares. And the amazing thing is that during the GeV flare, even in a deep Chandra observation, you don't see any change in the nebula. So these gamma rays are coming from a very small region. We don't really understand it. It probably has something to do with magnetic reconnections, since pulsar is inherently a magnetic object with knots having some kind of shocks and maybe relativistic boosting. But it's an interesting object, and we're going to hear more about it at this conference. So I think the open questions, as I'm going through some of these topics, I wrote down a few questions. We'll certainly revisit this when we're looking at key questions for the future. Where is the acceleration taking place? What's the mechanism? And why is it predominantly or only in gamma rays? That's really bizarre. I turn to one of my favorite objects, which are gamma ray bursts. LAT has now detected 46 long bursts and 3 short bursts, so it's getting quite a good statistical sample together. And almost every one of these shows the same characteristic, that the high energy gamma rays are delayed and extended compared to what you see at lower energy gamma rays. So here's a good example. This was a short burst, 090510. The GBM instrument on Fermi measures the low energy light curve. You see how you can see structure even in this short burst. But then the high energy photons tend to come later, and they start later. In fact, comparing the arrival time, even though they start later, still all of the photons are arriving within a couple of seconds. This object is at 7 billion light years away. So it's it's very far away, and you might guess that there'd be some dispersion between the lower energy gamma rays and the higher energy gamma rays, and we see none. So it's to a factor of 1 in 10 to the 16. So light travels the same speed across this whole wavelength band. Also, it looks like new spectral components are needed to explain the GeV emission. I just show here a model that shows, this is the band spectrum that we've been used to for many decades now. And we're beginning to realize that there's other components to the spectrum that come in and are necessary to explain the high energy emission. This is a new burst that was observed. This is from April 27th. And there have been 5 papers on this burst submitted to Science magazine. We're waiting to hear if they're all going to be accepted. But it was observed by Fermi Swift. It was the first time a hard X-ray afterglow was detected with NuSTAR. And the small optical telescope at Los Alamos, Raptor, was observing that spot of the sky as the burst was going off. And so it detected a bright optical flash at the beginning. And there's a lot of things we've learned, and a lot of things fit with the models, but I'm trying in this talk to point out things that are unexpected. And so here's one of the unexpected results. Since we have so much data, we can do accurate modeling of the spectrum. And afterglow spectra are typically seen to be synchrotron, fit by a synchrotron model. But here at late times, we're seeing LAT photons that are well above the maximum synchrotron model. And so, where are these photons coming from? Are these photons part of the prompt emission that are somehow the prompt emission keeps going? Or are they part of the afterglow emission, but there's some other component that's coming in? One of the things that we've learned from the Swift satellite is that short gamma ray bursts have very different origins than long gamma ray bursts. We think there's pretty good evidence now that they're due to neutron star or neutron star mergers, perhaps black hole neutron star, and they coalesce and produce a fiery explosion which produces jets, just like the long burst does, but the long burst is from a black hole that's formed at the center of a massive star, and these jets beat their way out of the star. So the origin is very different. In both cases, though, you make black holes and there's an accretion disk that forms, at least that's what we believed. But if you look at the properties of the gamma ray burst, they're remarkably the same. We see afterglow. We see flares in the afterglow. The short bursts tend to have weaker afterglow, but they still have afterglow. And look at these light curves. They're on very different time scales. This is 50 seconds and this is 0.5 seconds. But they look similar. They're highly variable. They turn off, they turn back on. And so it appears that whatever the central engine is, you dump all this energy into this small region, probably create a black hole, an accretion disk, and after that, the jet is launched and the physics is the same. So there's something very profound about how particles behave as they are produced in such jets. There's an evolving paradigm. We just did a small workshop in Stockholm, and Peter Meseros was talking about this. How the old paradigm was internal shocks produce the gamma ray burst. So you have this central engine, it produces an outflow of particles in a beam. Shocks are formed, the shocks interact with each other to accelerate particles to make the prompt emission. And then the shocks interact with the external medium, external shocks, to produce the afterglow. But this model has always had problems, both in the data and from the modeling standpoint. It's just, it's radiatively, the internal shocks are radiatively inefficient. And there's turbulence that comes up that interrupts these shock interactions. So the new idea is that there's a photosphere that's fairly radiated. There's magnetic dissipation taking place. And so you've got this raging fireball, and when it breaks out in the photosphere, a lot of photons are produced in shocks. And then there's magnetism that's much more important than we thought before. And we're going to hear a lot more about magnetic reconnection and magnetism later talks. I listed here some of the key questions for gamma ray bursts. How much are they beamed? We really don't have very good data. We think they're beamed. We have some evidence. What's the process? What is the acceleration mechanism for this prompt emission? We don't know, and there's a very in all kinds of accreting sources like this, especially black holes, are the outflow photonic or hadronic in nature, or some combination. And very new question, what's the role of magnetic fields? Could we build polarimeters to really measure what kind of magnetic fields we have and what their effect is? Then there's some other questions that don't have to do with particle acceleration, but really causes short gamma ray bursts. Maybe they'll be coincident with LIGO, Virgo events, and so we'll see that they're really mergers. And what's the nature of the distant stars in the universe, POP3 stars? Some models say that they make very bright gamma ray bursts, and it would be one of the best ways to detect those distant objects. And so now finally I wanted to turn to active galaxies. So this shows the point sources that we have in the second Fermi catalog. There's almost 2,000 of them. Some of them are, many of them are along the galactic plane. We're seeing more and more pulsars, particularly millisecond pulsars, are found with very high efficiency over the last year. But then, and 1/3 of these sources are unidentified, or a more popular way of saying it this way these days is that they do not have an identified counterpart at other wavelengths. So there's a lot of mystery here about what's going on in the sky with 1/3 of the sources that we don't understand. There may be new classes. Most of these high latitude sources are understood, and they're AGNs, they're beamed AGNs in almost all cases. They're either flat spectrum radio quasars or BL-LAC type objects, so they have jetted emission. This is a paper came out 2 years ago, but it's a really nice study. Again, it's a multi-wavelength study of a blazar using the first 2 years of LAT data from 2008 to 2010. Of course, we had Fermi continuous coverage through that time. So here's the light curve you see from the Fermi LAT, but then it was multi-wavelength data showing the light curves all across the wavelength band. We're learning a lot from these blazar observations on constraining the Lorentz factor. It appears this isn't a great surprise, but our data are consistent with Lorentz factors of 10 or 20, and electron and proton components of the disk, what makes up the jets that are coming out. One of the things we don't understand, I mentioned I want to highlight these, are certainly the correlations are not very well understood. You can just see with your eye that when there's a flare at one wavelength band, you tend not to be at this flare in the other wavelength band. There are some correlations that we see, but they're not very well understood. And also, if you look at the modeling that's done with these two component models and see how it changes with time, so time resolved spectroscopy, you'll see some of these points, like the X-ray points, don't fit on the model for that period D. And so it's telling us that there are other components going on. We really still don't understand very well where in the jet this this emission is taking place. We discovered a very interesting transient with Swift that has to do with blazars. I'll show you how that works. It was completely unexpected, another one of those questions of where did this come from. It looked like a gamma ray burst, but it lasted for 2 days instead of 60 seconds. It was highly erratic. We didn't get data filling in all this time, but you can see how it was bouncing all around. And then it smoothed out and it decayed. We observed it for about a year. Just recently, it seems to have dropped off. One of the clues, actually Josh Bloom was the first person to notice this. There was a counterpart seen at optical wavelengths, and it was right at the center of a fairly nearby galaxy, a redshift of 0.5. But this wasn't a known AGN. It wasn't an accreting black hole. It seemed to be a dormant black hole at the center of this object. And it looked like this was best explained as a tidal disruption event. So here's the black hole sitting at the center of the galaxy. The star comes within the tidal disruption radius. This poor innocent star, and is totally torn apart. And what it did in this case is it produced an accretion disk, as you'd expect. There's theories predicting this, but then it launched a jet. And we saw this as such bright variable gamma ray emission because we were looking down the axis of the jet. It had just happened fortuitously to catch this. And so this is actually seen, you could think of it as seeing a blazar suddenly being turned on or suddenly being produced. It's certainly the onset of a relativistic jet around a massive black hole. So some of the key questions in the blazar field. Now, what is the source region for the different spectral components? As I showed you, there's very poor understanding of that. This is a long-standing question that there have been in the AGN field. Are the jets leptonic or hadronic? What's the cause of the high variability that we typically see in blazars that are jetted toward us? And in flat spectrum radio quasars show the same thing. And what's the prevalence of jetted tidal disruption events? After we saw this one event 2 years ago, we've been looking more carefully in the Swift data to see if there were some others that we missed. And we think there is another one. And then there have been 3 or 4 papers this last year of people looking with X-ray data and believe that there may be more of these. But they're still going to be rare because you have to be in the jet to see that bright emission. And how important is magnetism? What can be learned from gamma ray polarization measurements? And then this isn't really about particle acceleration, but or maybe it is, what are the unidentified LAT sources? There's a lot of work that it'll take many years to try to understand each one of those with multi-wavelength data and looking at the variability. I put these down in a way I wanted to move from key questions to thinking about hardware for just a little bit. But instead of looking at key questions, sort of what are the topics that cut across these different areas? Beaming and jetted sources. What do you need to resolve that? You need multi-wavelength data over long periods of time so you can do the correlation analyses. Then comes the elephant, right?
Exactly.
Okay. Variability in jetted sources. This applies to all of these. You need continuous monitoring. So whatever we want to build in the future should be like Fermi, that it covers a lot of the sky all the time. Leptonic versus hadronic outflows. This is difficult. Modeling has a lot to do with this in theory, but multi-wavelength observations during the prompt emission, it's really hard, like for a gamma ray burst, to get optical data during the prompt emission because optical telescopes tend to have a small field of view if they're sensitive. And so you either need very rapidly slewing telescopes or ones like Raptor that have a wide field of view. Internal versus external shock models. This is, it's always been a key puzzle and topic, but now there's a lot of interest, renewed interest in this area. And again, you need multi-wavelength observations, particularly in the X-ray, optical through high-energy gamma ray during the prompt. Reconnection in pulsars and gamma ray bursts. Magnetic reconnection models are, magnetic full models are becoming more common, and so we're learning more about that from a theoretical and modeling point of view. And can we use a gamma ray polarimeter, X-ray or gamma ray polarimeters in the future to really try to make measurements related to the magnetic outflows. And then there's a lot of things that don't have to do with particle acceleration, like the nature of the dark matter gamma ray lines. Are we really seeing them or not? Or if we had a more sensitive spectrometer, could we really get down to a point of making very constraining measurements or finding the lines? The origin of the short gamma ray bursts. I mentioned some of these other things. And so I know we're really talking about science at this conference, but I did want to make this one comment about sort of collaboration between agencies. I think Fermi is a brilliant model of what KIPAC, SLAC, and the DOE can do when you combine two different agencies and two different groups of people. And so DOE should continue involvement in leading and partnering, or the other way around, with NASA and NSF experiments with scientific themes that are relevant to DOE. So just a few examples. We really need to start now thinking about what a future mission beyond Fermi is going to look like. One thing Fermi doesn't do very well is look below 200 or 100 MeV. The point spread function is really large there. So that might be an area to pursue. You could do dark matter, particle acceleration. A future gamma ray observatory. We also need to think about gamma ray burst observatory. And then, of course, CTA, LSST, these do have involvement here at SLAC. And WFIRST is an opportunity, perhaps, to have combination of NASA and DOE working together like we originally were with JDAM. So, thank you.